Hello, this video explains the lecture part of Lab 6. Lab 6 is about diodes. We're first going to introduce diodes as a circuit component, and then we're going to learn some basic applications for the diode. Here on the right hand side you see a figure explaining the diode circuit symbol as well as a picture of a real diode. You can also see the anode and the cathode and where they're located with respect to the diode symbol and how the current normally flows within the diode. A diode generally conducts current in only one direction. So here you see the IV curve of an ideal diode. So if you are to plot the current versus the voltage of a diode, this is the curve you're going to get of an ideal diode. So for example, if the voltage across the diode is less than 0, which is this part, so this is if the voltage is less than 0, then that means there is 0 current flowing through the diode. Here on the right hand side, the voltage across the diode is greater than or equal to 0. That's why there is current flowing through it, and the current will depend on the rest of the circuit. However, for a regular diode or a non-ideal or a real life diode, this is the IV curve that you will see. You'll notice that, just going to erase this, you'll notice that the diode will start conducting currents once the voltage across it reaches what's called the threshold voltage or the diode voltage. Usually it's denoted by VD. Normally VD for a regular diode is equal to approximately 0.7 volts. So once the voltage across the diode exceeds 0.7 volts, that is when it will start conducting currents. When the voltage across the diode is below that, then it will not conduct currents, or that means the current going through it is equal to 0, so it will act like an open circuit. So we could say that when the voltage across a diode is less than VD, and we know that VD is equal to 0.7 volts for a regular diode, that means I is equal to 0, or you can say that the diode acts as an open circuit, OC, open circuit. When the voltage across the diode exceeds the threshold voltage VD, then it will act as a short. Then the diode will act as a short. Short circuit. That means it will start conducting current across it. Notice that the polarity of the diode is always going to be positive, negative here as explained in the figure. And we're going to assume this current flow direction. Normally when the diode or the voltage across the diode is positive, we'll say that the diode is forward biased, and when the voltage across the diode is negative, we'll say that the diode is reverse biased. The first application for a diode we'll introduce today is a half-wave rectifier. On the left-hand side you see one of the circuits for a half-wave rectifier. This is called the positive half-wave rectifier. That means it will filter out the negative half of the input and only outputs the positive part. Here in this figure you'll see the plot of Vn, the input circuit, which is this sinusoidal input. Notice that it will have positive half at some point, and then it will start to become negative here. When the input Vn is positive, then the voltage across the diode is also going to be positive if you apply kVL here, then that is when current will start flowing through the diode as well as through the resistor connected at the output. This way V out is going to almost be equal to V in, and if you want to be more precise, you could say that V out is equal to V in minus VT, right? Or the peak of V out. So here, since diodes generally only connect or conduct current when they're forward biased, or only when the voltage across them is greater than the threshold voltage 0.7 volts, then they will start conducting currents. Otherwise, if the input is negative, so during the negative half cycle of the input, then the voltage across the diode is going to be negative or less than 0, less than 0.7 actually, when it is less than 0.7 volts. Or we could say 0 for short, or if we want to round, we could say if it's less than 0 or if it is negative, then that's when the diode is going to act as an open circuit, so the current here will be equal to 0. I is equal to 0. And if you apply Ohm's law, you'll find out that V out is equal to 0 as well. So V out is equal to IR, and we know that I is 0, that's why the out is going to be 0 during the negative half cycle. So this is how the half-wave rectifier circuit works. Here, this is another application of the diodes. It's called a full-wave rectifier. So depending on the knowledge on a half-wave rectifier, here instead of using just only one diode, we're using a total of 4 diodes. So only 2 will work at a time. So when the input is positive, then current will flow in this direction first, and then through the resistor, and then it will go back to this diode and then back to the input, and so on. And during the negative cycle, or the negative half of the input, then current will flow through. Current will start to flow here first, and then through the resistor, and then through here back to the input. We'll explain the full wave rectifier further next week in lab 7, in which we're also gonna simulate the full wave rectifier and find out ways on how to improve it. There are further applications to the diodes. The next one is the clip-in circuit, also known as the clipper. The reason why it's called the clipper because it clips the output at a certain voltage. You have a combination of 4 circuits, but they're all similar if you notice. They all depend on a diode, a DC voltage, and an alternative signal as an input. So here you'll see that the circuit depends on a DC input voltage, the diode, and an alternative signal as an input. If you notice, the output for the clipper circuit is always measured across the diode and the DC offset voltage. And observe that the diode only either conducts current or it doesn't. So you can say that it will either act as a short or as an open circuit. So we're always going to consider the 2 cases. The first one is the case where the diode acts as a short, or when it will conduct currents. So when it acts as a short, then V out is going to be equal to V. Using just your knowledge on circuits or ELEC 220, you'll figure out that when the diode is forward biased, or when when its voltage or when the voltage across it is greater than VD, then V out is equal to V. Otherwise, when the diode acts as an open circuit, then you can maybe cut open the circuit here. So when the diode acts as an open circuit, what you're going to measure to evaluate the output is the voltage across R and the voltage across Vn. So the input is going to look exactly like Vn. Notice that in all 4 circuits, the input voltage is actually a sinusoidal signal. So it looks like this. Okay, except at the output, you're going to clip the output or the input voltage at V. Depending on the polarity of V, you'll notice that V could be a negative voltage or a positive voltage. Here, notice, for example, in this circuit, V is less than 0, right? And here you also clip the output at V, except that V is less than 0 or happen to be less than 0, and so on. The rest of the circuits are all the same, except here, for example, the polarity of the diode is different. Notice that the current only flows in this direction for this diode, this direction for this diode, and then towards the bottom for this diode, and so on. So let's examine this circuit as an example. We're also going to cover 2 cases. The first is when the diode conducts. So when the diode conducts, V out is going to be equal to V, right? So this is when the diode is on. When the diode is on. You can also say that the diode is on or off. So on means forward biased, or the voltage across it is greater than or equal to VD. When we say the diode is off, it means that the diode doesn't conduct current, or alternatively, it also means that the diode is reverse biased, or the voltage across it is less than VD. So the first case is when the diode is on, that means V out is going to be equal to V. The second case is when the diode is off. That means it doesn't conduct current, or it acts as an open circuit. That means we're going to read V out from here, and it's also going to be equal to Vn. The last application we're going to cover for diodes is the clamper circuit. Its whole purpose is to shift the signal up or down such that it sets a maximum value at the output or a minimum value at the output, depending on the circuit configuration. So let's examine 2 cases. One in which we're setting the output, or we're fixing the maximum value of the output. Here, again, there's 2 cases. First case is the diode is on, or it acts as a short. That means V out is going to be equal to V. So for all of these cases, V out is going to be equal to V. And one more thing, notice here you have a charging component, which is the capacitor. So when the diode conducts, or when it is forward biased, the capacitor is going to charge to a value equal to, so we'll call it Vc. V stored by the capacitor is going to have a value equals to the peak value of the input. The reason why we set the peak value is because the diode is forward biased only when Vn is equal is the positive, is acting during the positive half cycle. That's why when the diode is on for the circuit configuration, the capacitor's voltage is going to be equal to Vp. Right? Now, during the negative half cycle, the diode is going to act as an open circuit, so let's remove it from the circuit and say the diode is off. Then you're gonna read the output voltage through here, and it's simply gonna be equal to negative VC actually. It's gonna be equal to negative VC plus Vn. Hence, the output, if you notice, of this circuit is equal to the input shifted down by a value equals to Vp plus Vn. And we said that earlier that Vc is equal to Vp. So this is where the negative Vp came from. And next we're going to explain one case in which the circuit is configured to set Vout minimum at a certain value. Observe that the difference between this circuit schematic and this one is that the diode in here is pointing up. That means the current is going to flow in this direction, so that means the diode is going to conduct current during the negative half cycle of the input. So if you just do the analysis that we just did earlier on this circuit, you'll find out that Vout is going to be equal to the input voltage plus the peak voltage of the input minus this V. So if you notice that this V is actually the magnitude of the DC offset here. Vp is the peak value of Vn. So it's also a DC value, and Vn is of course the shape of the alternating signal, or the AC input actually. This concludes the lecture part for lab 6, which is about diodes. In the lab sheet for today's lab, we're gonna need to do some plotting using MATLAB. Remember to use MATLAB Live or MATLAB Online. There is code that's already written in the lab sheet that will help you do the plotting. So if you need further help regarding how to plot, please leave questions in the chat within the live session if you're online. Otherwise, refer to the hint that's in the lab sheet itself. And for now, we can download the lab 5 sheet from Moodle. Start working on Multisim Live, and make sure that before you submit any work or before you even leave the chat or leave the session, make sure that you have your work checked by me and submitted to Moodle within the lab hours themselves. Also, regarding completing the worksheet, make sure you complete it individually and you have your name typed in the header of the file. And if you prefer to, you could still write your lab report with your teammate. And finally, if you're done or you're still working but you need help, feel free to ask or to request to share your screen with me so I can see what the issue is and help you with it. And please don't close Multisim page before you have your work checked. Thank you for watching. If you're still in the live session and you have a question, please leave your questions in the chat. Otherwise, you may email me via alt@auk.edu.kw. Thank you and good luck.